Hello, hello. This is building my own DBMS in C++. Today I'll be trying to implement B trees. I am not sure how will it go. I hope it will go fine, but we'll see. We'll see. I opened some article in Programmers. I hope it's fine to stream it. I hope so. Yeah, we'll see. And before that, I have some what's called. I have something to change here. My girlfriend recommended it. It's not. It's in table. This part it can be more compact, so to say. So const expr. I mean, it is fine if I put it in this const expr. I put it or I can just do a get t here. I think. You know what? I'm even gonna check it. I'm even gonna check it. Because she did send me how to do it. Just a second. Okay. I don't even need to do the get. Just to string on the current entry. Okay. So we have this stud variant, right? I don't need to get because I'm not using this, right? So here, oops. If const expr, const expr stud is same t int value, or oh my god, so I didn't check the camera. I hope it's fine, right? It's fine. I think so. Yeah. Okay. My my keyboard changed positions. I can't type. So stud is same t double value. Okay, so if it's double or int, I can just entries to log plus equals stud to string current entry, and it should work if I understood it correctly. Yeah, and else it's just stud to string current entry, right? Yeah, not to string, oops. Entries to log plus equals current entry. Okay, and let's comment this out. I don't this Okay. So it should work. Oh, well, let's build. Oh, right. Yeah. I don't want. I'm gonna rewrite it anyway. So yeah, I think I can just delete it for now. Is it pragma 1? Yeah, it is. Okay. Okay. 0. Nice, nice. And let's run it. I have just let's delete this. Okay, and let's run it. I think it's this one, right? Oh no, debug. Okay, and nice. It logs everything again, just to be sure. Yup. Nice. Amazing. Okay, thanks to my girlfriend. This is much more compact and readable. So nice, and I learned a new thing. Const expert. I mean, I knew the idea of const expert. I didn't know how it works. So I'm gonna just say what I understood. So take it with a grain of salt, and obviously fact check me. So const expert is usually a suggestion to the compiler. You can just say, nah, I won't treat it as const expert. The compiler also may treat a lot of things as const expert without writing const expert, so the compiler decides. And const expert, from my understanding, is this is evaluated at compile time, not at runtime. So this also, const expert is evaluated at compile time. I think you can hear that. That's my father. Yeah. He's fine. He's alive. It's how it's called. A chew. I forgot how it's called in English, but he's doing the chew. I'm sorry. Anyway, const expert is evaluated at compile time. I will, you know what? I will make it more. I'll also check if. Wait, maybe you can hear my keyboard, but not that much. It's just really loud. I'm sorry. Anyway, const expert is evaluated at compile time. But it's a suggestion. The compiler can say, no, I can't evaluate it at compile time, or I don't know, no, I don't want to evaluate at compile time. But this is not if const expert is a special case, okay? It's not a suggestion. You're telling the compiler this is evaluated at compile time, like you have to, or don't compile it. Like tell me there's a problem, like you can't evaluate at compile time. And what it does is basically it, in case of stud variant, it creates, like, I have int, double, string, and char. So this is just this line of code is pasted when there's an int or a double in while it's compiling. Like there's a, I think it's tables. I don't remember how stud visit exactly works, or I think I remember stud visit was something like virtual functions. I read it somewhere. I don't remember. Anyway, this is basically when it's int or double, this is pasted there, right? And when it's string or char, this is pasted there, basically. So yeah, this I'm explaining it poorly because I try to remember uh, what I understood. But anyway, basically, yeah. So the compiler, with especially with how it's called, like with stud visit, uh, it like creates four different chunks of code, um, which are the same, but um, with t being replaced by the how it's called by the I forgot type. Oh, I'm sorry, by the type. So the t is getting replaced by the type. So in my case, it creates like four tables uh, each replaces like the t with char, then with string, then with int and double. And for the tables or chunks of code where this is int or double, this is compiled. And the chunks where it is char or string, this is compiled. So that's how const explorer works in my understanding. And I gotta put my phone on do not disturb. I am sorry. Okay. Um, so this is how I understand it. Again, fact check me. Uh, and if I'm wrong, please correct me in the comments or here on stream if you know correct me, and I'll correct myself. I'll see, like, I'll research it again myself and see if where I was wrong. So anyway, this is it for the logger for now. Obviously, there are some, like, there are more of the logger to add. But, well, first of all, I need to think about it more. Second of all, it's probably will be at a different place, not here at the table. I'll probably also change it somehow, somewhere when down the line. So now we got it. We're getting to know B trees, to know, to learn. I'm gonna try to learn B trees. My current tasks is this is, by the way, need to add new. That's today is first. I have to 0106, and I don't know why I checked. I don't know why I checked the year. Best viewers on, what does that mean even? Okay, I think that's a spam bot. Oh, do I need to open the? Oh, okay. How do I? Nice. Okay. Yeah, sorry for that. I mean, I'm sorry if I didn't understand your message, but it seemed just like viewbotting, I think. You know what? I'm not gonna do that for everything. I'm just, yeah. Maybe wait. What if I can I just? No, it doesn't work. Okay, I'll edit later. Anyway, this. Oh, and you know what? I'll add. I'll add it to Git. So Git add everything. Git commit. Um. Uh. Table state log. How you call it? How you call the change? Like, it's doing the same. It's not a bug. It's just like less code. Compacted. Sure. Compacted. Did I erase the? Yeah. Okay. I did. So yeah. Mm -hmm. Nice. Okay. So now tasks. My current task. So I have user input. It will be way down the line, I think. But definitely not today. Transaction logs. Command. This also. But today is mainly B-trees. I'm searching. So add database that will store related tables. Data storage on file for tables. For databases. This is kind of. I'm still not sure how I will store the data on tables. By the way, I need to make chat text smaller. I think. I'm sorry. Yeah. Font size. I hope it's not too small. It's test. Test. I'm not logged in. I mean, I'm not logged in my Streamlabs. Sorry. Test. Yeah, it's small enough, I guess. It's kind of not centered though. Can I like? Sorry. I mean, it's fine, right? For now, it's fine. It'll be fine. Anyway, so I'm not sure exactly how to store the tables and databases. Okay, I need first of all, I need to, where is it? Table HPP. I need to decide what I'm doing with this. Table name is easy. ID, I'm not sure how I. No, we'll figure it out later. Anyway, so the way to store tables at file should be like, what is this? The way to store table at files should be like I think in different folders, right? Different folders, different databases. A folder is a database and a page is a table, I think. Right? That's the terminology. I am not sure. And I'm not a pro at databases or anything. I'm learning databases right now, basically. Uh, so yeah, I'm not sure about like these tasks. They will be probably changed. This is definitely to stay. You know what? I'm gonna erase those. I don't need it. I mean, this kind of covers everything, right? Uh, this I don't need right now. Just implement b3. This is what I will work on. So move it to the top. Okay. So yeah. Also, with this. I mean, if I somehow finish this today, then I'll move into doing this. Move doing this. After batteries is basically is storage, right? So I have again. I hope I can stream it. I have a program is let's open here in Chrome. Will I hope I remember switch back. It will be super embarrassing if I want. So I hope to remember that. Anyway, so I'm gonna read it, and then I also have an implementation here in Python, Java, C, and C++. So I can read and try to understand it. Okay. So by the way, I think this is just programming is a good learning. So that's what I heard from like on Reddit stuff. Like people usually ask where to learn C++. I didn't learn from programmers. I learned from different sources. I read a book. I read a 700-page book about C++. But I think this is a good one for learning C++ because I heard a lot of people recommend it. So yeah, let's get into it. So B-tree is a special type of self-balancing search tree in which each node can contain more than one key and can have more than two children. It is a generalized form of the binary search tree. So binary search tree, if you don't know, it's basically, you'll even open it. It's like everything that is smaller goes to left, everything that is bigger goes to the right, or it can be like reversed, right? It also can be, and the root is the middle one, right? The middle one. So if we want to find 4, we go 8, then smaller than 8, 4 is smaller than it, then we go left. Then 4, again, we're searching 4, so 4 is bigger than 3, then we go right. And 4 is smaller than 6, then we go left. And we find 4. So, yeah, there is a... You have to self-balance it. Like, you have to balance it when you insert. Right? There's a... I don't remember it. Like, insert operations. Like, you have to change the tree around. I hope I don't need to know that for this to understand the B-tree. But if I don't, I'll go to the binary tree and implement it, and then there implement the B-tree. So why do we need B-tree data structure? The need for B-tree arose with the rise in the need of lesser time in accessing physical storage media like hard disk. Secondary storage devices are slower with a larger capacity. So secondary are your SSDs, HDD, the slower one, the slower one. today it's mostly SSDs, right? So you have like you can have 1, 2, 3 terabytes of data storage, but they're slow, and there's random access. The RAM, right? It it doesn't have a lot of storage, so you have the 8 giga or gigabytes. I'll say gigabytes. Gigabyte sounds better in my head. So you have 8 gigabytes, 16 even. Sometimes, I mean 16. I think today 16 is where most people at. There's 32 and 64. I think is considered a lot today. So yeah, 64 gigabytes and 2 terabytes are different, like orders of magnitude. So when you need large data, like a lot of data, sorry, a lot of data, you can't really store it on RAM. But the RAM is not just smaller; it's way faster though. So ideally, if you can, you want to store it on the RAM, but it's not most cases. Like most cases for databases, it's not plausible because it is like you need a lot of storage for tables. I don't think I will create enough tables for gigabytes and gigabytes of data, but things like SQL, like MySQL and stuff like that, where companies can create large chunks of data. I want to check is the borders okay? Yeah, they seem fine, right? Okay. Sorry about that. I wanted to check if, because the borders my Streamlabs seems kind of wonky, but it seems fine on stream. Okay. So yeah. Other data structures such as binary search tree, AVL trees, and red black tree. I heard about them. I don't see an implementation or what they exactly do. Etc. can store only one key in one node. If you have to store a large number of keys, then the height of such tree becomes very large and the access time increases. However, B-tree can store many keys in a single node and can have multiple child nodes. This decreases the height significantly, allowing faster disk access. B-tree's properties. For each node X, the keys are stored in increasing order. For each node, the keys are stored in increasing order. Okay, so yeah. In each node, there is a Boolean value x.leaf, which is true if x is a leaf. X. I'm saying x, but I think it's in English it's x. I'll say x. If n is the order of the tree, each internal node can contain at most n-1 keys, along with a pointer to each child. At most n-1 keys, along with a pointer to each child. Each node except root can have at most n children and at least n divided by 2 children. All leaves have the same depth, i.e. height h of the tree. All leaves. Oh, okay, yeah. So it's gotta be like you can't have. Yeah. In here. So you can't have that because it's a leaf and this is a leaf and not on the same level. That's what it means. So the root has at least 2 children, yeah, and contains a minimum of 1 key. So yeah, root gotta have at least 2 children, because if it only have 1 child, then this child is a leaf. And wait, I mean there's no other leaves, but okay. The root has at least 2 children, and if n bigger or equal than 1, then for any key b tree, what the any n key, I mean nth key b tree of height h and minimum degree t bigger or equal than 2, h is bigger or equal log t n plus 1 divided by 2. I have no fucking idea what that means. What's the degree of a tree? Degree of a tree. Right, degree is the in the tree data structure is the total number of children of a node. It's called the degree of a node. Okay, so the total number of children of a node. Degree of a node. And what's the degree of a tree? The highest degree of the node among all nodes in a tree is called the degree of tree. Okay. I need to I need to read to the end. I was like, okay, I understood that, and then I didn't understand everything. So if n bigger or equal than 1, right, n is the order. What's the order? Order of a tree in data structures. Root node said to have order is the level. Okay, is depth, and the root node children are at level 1. So that's okay. That's the depth, right? Right. If n is more or equals 1, then for any n key, so n is the current order. Okay, so of and the root is 0. So basically it says it's not the root if the node is not a root of height. Wait, height h. What the fuck? I thought order is the height. Edge. The necessity for tree. I don't care. Just give me tree terminology. Okay. Root, parent, blah blah blah, child, siblings, leaf, internal nodes, degree is total number of children, right, level, the root 0 and the root's node children at level 1, height, so what's depth and level are the same, and many edges from the root node are called the depth of the tree. Number of edges from the node from root node to the leaf node in the longest path is known as depth of tree. What's path? It's kind of the same. I mean, I'm guessing if it's not self-balancing and always the same, lists are the same level, I guess, right? So, okay, we have here, node dish. Here we have n is the order. So if the order, where is order? I have no idea what's order. I'm guessing it's level. So n is the tree. Each internal node can contain at most. So I'm guessing bigger than equal than 1, it's not root, right? And then it says height h and minimum degree. So height is number of edges from the leaf node to the particular node in the longest path known as the height of that node. In the tree, the height of the root node is called height of tree. The tree height of all leaf nodes is 0. So 0, 1, 2, right? So, oh my god, this is annoying. So of height h at minimum degree of t bigger or equal than 2. Where is degree? Degree is total number of children node. Okay, so degree is number of children. So if it has more than or 2 children, then height is bigger or equal than log the amount of children of order of the tree. Order of tree? Divided by 2. Oh, I think I understand. I think I understand. So the amount of children, say each, says here for each node, the keys, sorry. Each internal node can contain at most n-1 key along the way. Each node except root have at most n children, at least n divided by 2 children. Okay, so the amount of children of each internal node is each internal node can contain at most n-1 keys along with a pointer to each child. I think, okay. n-1 is the amount of keys. Between n and n divided by 2 is amount of children. So the height is bigger or equal than log of the degree of the degree, which is, as we saw, the amount of children. So makes sense, right? In a binary tree, the degree is 2, right? Everything has 2 children, or 1 or 0. But so basically, if it's not a leaf, because it can't have 1 children, right? n-1, sorry, between n children and at least between n divided by 2 and n children. So this means everything that is not a leaf or the root. Actually, no, root is in here, so not leaves. But root is not here, so yeah, okay. So height is bigger or equal than log of the degree, so the amount of children they contain, of n+1 divided by 2. So yeah, you can have at most between n and n divided by 2 children. So yeah, you have the height of it is I mean, I can understand that. I think of a way to explain it, because explaining will further my understanding of it. But anyway, yeah, so if I have a degree of Let me explain it. N can change, right? So, yeah, I'm adding more and it can change based on us and some maximum that has to be, right? So n plus 1 divided by 2, I'm guessing it is because okay, and order is level, right? Where was it? What is order in this such? This was in Stack Overflow. Let's see. Degree represents the lower bound on the number of children a node in the bit tree can have, except for the root, i.e. the minimum number of children possible. So degree is minimum. Okay, degree is the minimum. Minimum degree t okay. Whereas order represents the upper bound number of children. Okay, so this is the upper bound. Height h. So the height is bigger or equal. I mean, the minimum is log of the minimum degree, right? Which is here. Degree is the lower bound, so is degree. So t is the lower bound. And we put in here the order, so the maximum bound. So log minimum bound of maximum bound. Maximum is n though. Maximum is between n and n plus n divided by 2. Then shouldn't be divided. So anyway, this is the best I can explain it and understand it for now. Let's move on. Let's move on. I don't want to waste too much time on this. Oh, I got out. Sorry, just a moment. Oh shit. Table is bloody. I cut my elbow a bit with a razor, a bit earlier. I thought it's already. Oh, I thought I don't have. It still leaves a little bit of blood. It's fine though. I'll clean it up later. So, operations on a bit tree. Searching an element in a bit tree. Searching for an element in a bit tree is the generalized form of searching an element in a binary search tree. What do you mean generalized? The following steps are followed. Starting from the root node, compare k with the first key of the node. If k equals the first key of the node, return the node and the index. If k.leaf equals true, return null, i.e. not found. Wait, what? Starting from root node, compare k with the first key of the node. Why? What's key? What's k? Sorry, k is the k is the provided key, right? So search for this key. First k equals the first key of the node. Return the node and the index. If k.leaf equals true, return null. Why? I mean, I know. Okay. Okay, let's move on and try to understand why this. But if k is less than the first key of the root node, search the left child for this key recursively. Left child. Wait, that's binary search. Okay, that's not B-tree, right? So search left. If there is more than one key in current node and key oh okay. So if there are more than one key in the current node and k bigger than the first key, compare k with the next key in the node. If k is less than the next key, search the left child of this key, i.e. k lies in between the first and the second keys. Okay, so if it's bigger than the first and smaller than the next, then we search the left child of this key. Else search the right child of this key. Okay. Well, see, we'll understand with examples. Repeat steps 1 to 4 until the leaf is reached. Okay, search example. Let us search k equals 17, the tree below of degree 3. So degree again, let's see, degree is lower bound number of children. So we have to have at least 3 children, except the root. Root have 2 children, exactly, right? So in the tree below of degree 3, so k17, we have 11 here, right? So k is not found in the root, so compare it with the root key. Right, k is bigger than 11. Go to the right child of the root node. Compare k with 16. Since k bigger than 16, compare k with the next key, 18. Since k less... Since k... Since k is less than 18, k lies between 16 and 18. Right. Search in the right child of 16 or the left child of 18. So here. And k is found. Okay. Algorithm for searching an element. So while I equal less than n at x means number of keys in x node, and k is bigger or equal than key I x, do I equals I plus 1. But why bigger or equal? Don't you want bigger? If it's equal, you found it, no? I is less equal. Nx means number of keys in an x node. So sorry. Changing positions. So n at x means number of keys in x node. So number of keys in... So this is not... Okay, right. So if I less equals than n at x and k bigger equals than key I at x, key I... Oh, so the ith key, the ith key of this node, right? Do I equals I plus 1. So yeah, we find until the k is... Until k is less. So until k is less than the ith key, we're increasing the index. If I... What's I and x? N at x and k equals key I at x, then return xi. Return x and index. I and the ith node, right? Not node, sorry. I don't know what that means, but if k equals key I, the ith key. What's I and x? Equals is supposed to be equals like equals equals. If I equals node x and key equals the key item. If leaf, then return nil. Else return bit research CIX K. Aha. Do you understand? I'm sort of. I don't know what that means. So, okay, again. This searches while the given key nx means nx means number of keys in x node. Okay, so x is the node, right? And x means the number of keys in the current node. So, right, this is the upper bound. Like I'm searching till I reached the keys. And k bigger equal than key, ix. So the ith key in the node. Okay, if I'm guessing this is equal. So if I reached the maximum and k equals the key, then return this. Why do I have to reach the end? Why do I have to reach the end? So if I'm searching for 18 or 16, I'm searching for 16. So I find it here. I didn't reach the end, but I found it, right? So it will go here. It's 1, but it's pseudocode, so I'm guessing it's like 0, the first one, so 0, right? So here, so 1 is less or equal than 2. That is correct. And k is bigger equal than key I is also true. It's equal, actually, if I'm searching for 16, right? So I is increased. I'm in this key. I'm in 18. And now I is still less equal than nx, right? We have 2 keys. I is now 2. And k equal, and k bigger equal than k. That is false. So if, oh, hello, you is 69, 69, 69. Nice name. Nice name. Welcome. I'm reading about B-trees right now. So we're at 18 right now, but let's say we're searching for 16, right? So this is the while terminated. If I and x and k equals key ix, I is currently 2. So C++ click following a simple man. C++ is really cool. I agree. I agree. I hope you'll enjoy. Yeah. Currently, I'm sorry, but currently it's less C++. I have, sorry, I have here the code that I'm working on. So that's actually not the code. That's the code. All this. So yeah, but I want to implement C++ Bitrees in C++ for my DBMS. So currently I'm working on that. Actually, there is technically C++ code in here. That's the implementation of it, but I'm trying to understand pseudocode that is actually not C++. So, yeah. So, again, if we're searching for 16, problem is if it's bigger equal. I think it's not supposed to be equal. I think it's a mistake here, right? If it's bigger, if it's just bigger, right? So 16 is not bigger, then it will terminate. If I and x, I am guessing this is if I less equals nx. Again, a mistake, and k equals, so if I'm searching for 16, it will work, right? It will work if this is not bigger equals, it's just gotta be bigger. Then return, right? So no, and I found it. Okay, so let's search for, say, 20, 23 even, you know, let's search for 23. So 11, no, for 17, yeah, let's run this pseudo algorithm on 17. So 11, right? This is a root. So we have this, and k is bigger equal. The key is bigger, right? So I equals I plus 1. So we are at 2. If I'm guessing again, less equals than the amount of keys, and key is equal, I is not bigger. I is not less. I is bigger. So we gotta, yeah, so if it's a leaf, we return null, so we didn't find it. Else, return b3 cixk. So we are at I equals 2. So the second child, root, right, and k, passing the key down, right? So here, and then 16 and 18, right? We have 16 and 18, and we're searching for 17. So I less equals than nx, and k bigger equals than key ix. So, sorry, only bigger, not bigger equals. Actually, again, I think it's a mistake. Then I equals I plus 1. It is bigger. 17 is bigger than 16, so we are at 18. And I is less equal than 2. The I is 2 currently. Yeah. So I is 2. And k equals, ik is not equals. If it's a leaf, it is not a leaf. Else return b3 search cix. So I is 2. This is the second child. Right, and it is a leaf, but we find it here, so I less equals than 1, right? And key k bigger equals than bigger than 17. This is not bigger, right? This is not bigger, so it won't go in here. It will go here, so it will be still a 1. Then 1 less equals than 1, correct? And k equals the key, right? 17 key found. Then return x and I. Okay. Now we need insertion and deletion. Insertion and deletion is kind of scary for me here. If the tree is empty, allocate a root node and insert the key. Wait, inserting an element bit consists of 2 events. Searching an appropriate node to insert the element and splitting the node. If required, insertion operation always takes place in the bottom-up approach. So we're starting from bottom, I'm guessing, right? Bottom-up approach. Starting from the bottom. Is it? Wait. The comment is here. I'm sorry. I don't know why it's so, like, it's manual. Like, the comment only goes away when I'm changing the timer of the hide delay. What if I put 0? Is it memory? Yeah. What's always show messages? Okay. I hope it's fine now. Hope it's fine. Pom. Okay. Let us understand these events below. If the tree is empty, allocate a root node. Oh, by the way, I forgot to change the name of the stream. Sorry about that. How do I do that here? Layout mode. I'll change it from here, I guess. Right. Oh no, that's actually a fine name. Okay. That's fine, I think. Okay. I thought I'm naming it like what I'm doing today on stream, but I'm just general name. Although I'm guessing it's kind of misleading because there's not a lot of C++ in here. I'm sorry, UE696969. I think I also have delays with the messages. I'm sorry about that. Maybe I switch to OBS from Streamlabs. We'll see. So, right, if the tree is empty, allocate a root node and insert the key. Update the allowed number of keys in the node. Search the appropriate node for insertion. Update the allowed number of keys in the node. Search the appropriate node for insertion. If the node is full, follow the steps below. Insert the element in increasing order. Oh, I can change it here. Never mind. Sorry. Set the element in increasing order. Now there are elements greater than it. Now there are elements greater than its limit, so split at the median. Push the median key upward and make the left key as a left child and the right key as the right child. Node is not full, follow the steps below. Push the median key upwards and make the left key as the left child and the right key as the right child. Okay. If the node is not full, follow the steps below. Insert node in increasing order. Insert node. Okay. Let's understand the insertion operation with the illustration below. The elements to be inserted are 8, 9, 10, 11, 15, 20, 17. So first 8 is fine. Then we need to insert 9. But we are a root. But, right, we are a root, but we need, like, we need at least 2 children, right? So we have 2 keys at the root right now. Then we insert 10. Now we have 8, 9, 10. We split. If node is full, I think full here means, for the root at least, full means 3, right? 2, sorry. Full is 2 keys. So insert the element in increasing order. Okay, now there are elements greater than its limit, so split at the median. So we have 8, 9, 10. 9 is median. So split at the median. Push the median key upwards, so 9 is the root. And make the left key as a left child and the right key as a right child. So left key 8 and right is 10 and 11. Update the allowed number of keys in the node. Okay, search not proper node for insertion. 11. 11. So if node is full, I think the root node is full, right? So after updating it for having like left and right, we have only how it's called. So the maximum amount is 1. So we insert 11, 9, 11. I mean 9 or 11 can be the median, so I guess we're just taking the 9. Push the median key upward, so 9 is upward. Make the left key as a left child. We don't have a left key, and the right key as right child. Where are you from, if you don't mind me asking? Yeah, sure. I'm from Israel. I know it's kind of a hot topic right now, but yeah. Where are you from, if you don't mind me asking? So where was I? Push the median key upwards and make the left key as a child node and the right. How do we search for? Wait, we search from the bottom, right? So searching. If required, insertion operation always takes place in bottom approach. So how is 11 inserted in here? Oh, I know. Nice. We are neighbors. I'm from Egypt. Oh, that's cool. It's cool. Hello. I'm learning Hebrew at the moment. Oh, good luck. Good luck with that. It's I'm bad at Hebrew. I was born here and I'm bad at Hebrew. I'm really. I mean, not bad, right? I can communicate in Hebrew and everything, but I'm not the best at it. Let's say, especially writing. I think in some case, not cases, sorry. Um, I think my English in some places is better than my Hebrew. Maybe less speaking, but at least writing, I think. All I know is each. איך הולך. Yeah, it's how it's going. What's up? Yeah. Yeah, good luck with that. It's definitely a hard language to learn, but doable. Like not the hardest. Like I think it's somewhere in the middle of learning curves. I consumed a lot of English media for the past, so my English is more functional than Arabic. Yeah, that's basically me. I think age um from age 16, so something like that, or maybe even 13. So maybe I think also past 10 years, right? I'm 23 now. I watched only English and with English subtitles on English. Like I have Netflix and there's some Hebrew here there, I think, but a lot of it is not translated, so I learned it along the way. So school Arabic, I think I learned Arabic in school. Like it's mandatory. I think it's mandatory until 9th grade, and honestly, it was harder than Hebrew. Like it is harder than Hebrew by a mile. I think. There are some similar There's a lot of similarities, I think. I don't actually remember, but yeah, it's harder. So if you know Arabic, you'll be able to learn Hebrew. And yeah. Um. No, it doesn't display the messages here. Where is chat? High delay 3 seconds. Okay. They were written from right to left. Yeah, yeah. That is correct. But I think Arabic is, at least for me. I guess I knew Hebrew at the point I was learning Arabic, but Arabic seems harder than Hebrew. But yeah, they share the same origin, right? Um, I also know Russian. Yeah, not writing though. Not in writing. I know how to speak Russian. Writing in Russian, especially cursive, is, I don't know how you read that, honestly. Like, have you seen Russian handwriting? It's the same symbol, basically. And they're like, yeah, that makes sense, yeah. So where was I? So 11. I'm guessing 11 is searching here. It is searching thing. So it's bigger than 9. I'm going here, and it is a leaf. So I'm inserting to the right of it. Then 15. 15 is inserted again. It's bigger, inserted to the right. But the maximum amount of keys is 2. So 11 goes up. It's 10, 15, okay, and then it is like that. Oh, goes up and splits it. Okay. Then 20. 20 is here. 2 keys are the allowed maxima, right? So it's fine. And yeah, 20 is bigger, so it goes to the right, the most right. 17 inserted in the middle here. Again, it's bigger than 11, so it goes here. Then it reached the maxima, so goes here to the root. So we have this, and we split those keys, and then here it is again at the root. It is at the maximum, so we take the 11 and split those two and bring this up, right? So again, so search the appropriate node for insertion. If the node is full, follow the steps below. Insert the element in increasing order. Now there are elements greater than its limit, so split at the median, right? Push the median key upwards and make the left key left child. So again, let's see what's going on here. So if we put in here 15, we take 11 as the median, right? 10 and 15 is now, like 10 is left of 11 and 15 is right from 11. And it goes up here, so yeah, left, right. Okay, I think I get it. I hope you also, for everyone's watching, got it. And on YouTube. So, why is it all green? Okay. Actually, let's look at. Let's look at code, not pseudocode. It's kind of. I think it will be easier, honestly. So, this is not C++. I mean, it is, but it's like. It's C. It looks more like C than C++, honestly. Like, why not use like a vector or something, or an array? I think it's more. I don't know. Let's see. Node double pointer. Why is no double pointer? Oh, wait. It's got a, right, it's got a point. Right, it's pointer of pointers. It's got to point to a bunch of, yeah. But again, it can be just vector of pointers, right? Okay. Int n is the maxima, maxima, and bool leaf. Public node int t, first key line, bool leaf. Not the first key, so that's key to insert. What's t? What is t? I give some better names. I mean, thank you for the tutorials and everything, but why don't they give better names? Fine. Oh, that's a node. Okay, that's a single node. Okay. Insert non-full. Okay, the key. Split child int I node y. So okay, and traverse. Friend class b3. Why is it a friend? You got a friend in me. So b3 has a root and t. What is t? I don't know. Public b3 int t, root equals null, t equals underscore t. Traverse, root traverse. Insert key. Okay, so t1 bool leaf 1. What? Who wrote this? You have the names here. You can like just okay. Leaf equals leaf 1. Fine. You also can do a what's it called? List initialization. Like, it's not hard. Keys, new int. Yeah, this is basically C. This is basically C. It's .c++. Let's look at Python code, honestly, just for understanding, and try to implement it myself. So self leaf equals false. I am not. I'm guessing. Yeah. Okay. So this is self leaf equals leaf. Self keys equals an empty array, and self child or list, I don't know how it's called in Python, and self child equals. So let's create a node. So that's a node, right? And that's the b3 itself. So self t, I'm gonna using t, so root equals b3 node true, right? So wait, what? Root is a leaf? Is root considered a leaf? Is root a leaf in data structure? If it is actually one question for single node, that node will in fact both root and leaf. Oh, I'm guessing they'll changing it. Makes sense. So yeah, when you initialize, the root will be the root will be a leaf. And self.t equals t. I still don't know what t is, but okay. Insert self. Okay, so that's insert node. Root equals self root. Okay. Length root keys root dot keys. So root is a b node, right? So root dot keys equals to 2 times self dot t minus 1. So t is the max. Oh, right. T is the amount of maximum. I think this is the amount of maximum nodes. Okay. Not nodes. It was 2 times blah blah blah. Where is it? Where is it? And is the order. So t is the order, I'm guessing, right? T is the order, so or half the order, I'm guessing, because it's root keys 2 times this. So length of root key, so the amount of keys equals twice the amount of demons, or I think T is okay. Big trees. I saw Geek for Geeks. I don't like it, but I saw. I think they explain what T is. T defined by the term minimum degree T. The value T depends upon disk block size. Right. So okay. So I'm guessing. Okay. So T is the minimum degree. So that's why it's 2 times T. So that's the minimum degree. 2 times this minus 1. And here the amount of keys I think it's also here explained. Every node except root must contain at least t minus 1 keys. The root may contain a minimum of 1 key. All nodes including root may contain at most 2 t minus 1 keys. Okay. So that's why it's here. I usually don't like Geeks for Geeks, but I mean for their code. But I seem to understand it. So the amount of keys, okay, so if the amount of keys equals this, so that's the maximum, temp equals b3 node, don't give it anything. Oh, that's false, okay. Okay, so self root equals temp child insert 0 root, temp child what's temp dot child? Oh, self temp dot child insert 0 root. Why 0? Wait, insert the key 0. It's the key 0. Or oh, that's Python. That's inserting at the list. So it's inserting 0. It's inserting at 0, right? At 0, inserting the root. Okay. Self split child dot switch at temp and 0. Temp 0. Why 0 though? X. Temp 0. Self insert non full. Temp K. Temp child insert 0 root. Self dot split child temp 0. didn't give an I, and there's not. What's going on here? Maybe let's look at pseudocode. So okay, I think I'll search for something else. Let's see beta versions. Is that the same? Right, that's the same. So that's the same. Self root equals temp, which is temp is not a leaf, but it got empty keys and empty child. Temp.child insert 0 root. Oh my god. What about this? Where's insert? Insert into K. Insert non-full. Bum. First search insert. Wait, what? B3. That's a tree node, right? And insert into K. Okay, insert root equals null. Then I'm creating a new root keys at 0 equals K. Yup. Root n equals 1. Okay, else, okay, it's not now, else. If root n equals 2 times t minus 1, then tree node s, new tree node t, false. T is the minimum. False, it's not a leaf. S c at 0 equals root. So that's children, right? S split child 0 root. Split child 0 root. Again, 0. Why 0? Int I, and that's okay. That's the index. Okay, so C0 split child 0 root. Int I equals 0 if s keys at 0 less than k, I plus plus s. What the fuck? If, oh, that's this if. Right, yeah, okay. So root equals s, and else sci insert non-full. Root s, else root insert non-full. Okay. Non-full. Okay. Else is if it is not equal to 2t minus 1. Insertion non-full. Int I equals n minus 1. If equals true. While I bigger equals 0 and keys at I bigger than k. Yeah, see, bigger, not bigger equal. Keys I plus 1 equals keys I. Um, the memory allocated? The memory is not allocated. I don't think this code works even. The memory is not allocated for keys, right? There's on their own devices, they're gonna be writing their own DBMS. I mean, what else can I? It's a good learning opportunity for me. Uh, I I learned a lot of C++ from this. Um, but yeah, I think I'm working on it like for at least 2 months, and it's going good. It's going good. Next thing, I write my own compiler or something. But yeah, it's always good to try and build like stuff that seems to be super hard and see where you can get with it. Ages ago, I was writing an API for MySQL using C. It was fun. Nice. It's C. I hate. Okay, I don't hate C, but I like. It's kind of, how do I say it? I love C++ and I don't love C. Uh, it it is very messy for me. Like I think I can write fairly. I don't know if I say clean, but readable and understandable code in C++, and in C I can't figure out how to write readable code even if it works. I I'm using C mainly for school projects. Like currently I'm learning C and Linux, and yeah, it's I'm getting I'm getting the A's, but because I know C++, not because I know C. The lack of feature is kind of a feature as it well defined. I guess you can say that. C++, on the other hand, I think there are I think there are too many features in C++. Like I don't think one person knows 50% of the features in C++. Like the standard library just gets bigger and bigger, and I don't know, especially the fact that they want always backward compatibility. So yeah, as long as you read a few books about software architecture, it was a fine experience. It is. It is. I love C++. I read a 700-page book on C++. It was fun, sort of, sort of fun. Still, it's 700 pages book. Software architecture. I didn't read a lot of. I didn't read books about software architecture. Um, I understand the basics, but yeah, I think it's like we made of Python and C. Uh, yeah, I heard a lot of people, um, but I don't think they actually code in Golang. I never used Golang. I heard from them that it's a good language that does things, but for some reason they call it boring. I don't know how a language can be boring exactly, but that's what I heard. Uh, I I don't think I will. It is boring. Why so? I don't think I will be leaving C++. It's really fun for me, even with its flaws. Uh, also Golang has garbage collector, which is not bad per se, but uh, I love collecting my own garbage, or or more often than not, shooting myself in the foot by not collecting my own garbage. um, yeah, where was I? So in here, like, by the way, this I don't think this works. Honestly, I don't think this works. I don't see where. Oh, never mind. I didn't see that. Okay, it it does work. Yeah. Okay. Search. Not search. Where is insert? Insert. Okay. So split child. 0 root. Keys 0. I plus plus s c at I, insert non-full k, root equals s. Okay, let's jump into it. Let's jump into it, and I'll just figure it out on the go. It's supposed to be a C++ stream, and I'm streaming for 1 hour and 40 minutes. Me reading this. So let's jump into the big tree. So here, it, by the way, I think my icons changed here. I think I'm using different extension now. I remember downloading it. Okay, never mind. Sorry. b3.hpp. Okay, so pragma once. I won't include anything for now, so let's just go struct b3. I don't know what the difference between a struct and a class, except that I know struct is a C thing. It was a C thing, so they added it for backward compatibility, I'm guessing. I know everything I know about difference between struct and a class in C++ is that without providing by default a struct, everything is public, and a class everything is private until you say otherwise. So that's everything I know about the differences between the two in C++. So let's. Oh wait, let's also go with struct node. Okay. So what a node have? Children, right? Yeah, children, keys. Let's see here. What was it? So children, keys, and minimum degree is. Degrees is in this, how it's called, in the bit tree itself. Oh, if it's a leaf, it's a leaf, right? So if it's a leaf or it's children and keys. So bool is leaf. What else? What else? not well. So I'm thinking about that because in there it was like pointer. I'm thinking of using just a vector. It's easier, honestly. So I'll include common HPP. So we have a vector now. So stud vector. Oh shit! Ow! This my desk gets bloodier and bloodier. Like I thought it closed. It is closed by now, but it is not. I'm guessing. So okay, whatever. So vector of children. So vector of nodes. Children. And vector of keys. Vector. Let's go with. I think size t. I'll go with size t. Keys. And this is supposed to be equal known, and let's this. The bool is leaf. 20 key, I guess, right? So size t key. Wait, let's see what they did in here. Keys temp. Bool leaf and temp. In here they did it. Where is the tree node? Tree node. Okay, so int t1 bool leaf t equals t1. Leaf equals leaf1. Keys equals new int. Right. Okay. So and this is an empty. Sorry, it is an empty. Called. It's supposed to be keys and children supposed to be empty with construction, right? Yeah. Maybe we want a copy constructor though, but it is later. Oh. Is t supposed to be constant, right? The minimum degree. T minimum degree. But again, isn't is setting t and leaf. Not setting n at all. Oh, it is. It's 0. I know what's n. I don't remember what's n actually. Where was it? N is the order of the tree. Each node can have content n minus 1 key. An amount of children? Think order is number of children. Right, number of children. Each n children, right. N is amount of children. So amount of children is size of this. And okay. And amount of kids is size of this. Okay. What else? So T is the minimum amount of children. Minimum? Yeah, minimum. Minimum. Yeah. And N. Okay, I'm trying to remember it as I go. I'm sorry if if it's a bit clunky, but I'm trying to understand on the way. So I do need minimum order, so let's have const static, right? Const static, const expr actually, no? Const expr static int min min children equals what was it? I think it's 128, right? It's supposed to be according to gigs for gigs, it's supposed to be the value of t. It depends upon disk block size. So I search for disk block size. A disk has a block size, which is the minimum amount of data that it can read or write. File system for disk or single disk available on this by dealing with blah blah blah. File system blocks are typically a few kilobytes, where disk blocks are normally 512 bytes. So I'm guessing it is based on the amount of bytes. So why did I take half? Oh, because that's the maximum, right? So 512. Okay, 512 will be the minimum. I think. It depends what's stored on the disk, right? Depends what's stored on the disk. So in my case, those are tables. So size of given size of is in bytes, right? Size of CP, size of operator, yield size in bytes, right? So actually, let's change this to size t, and then what is it? Depends on. So 512. That's a bit 3 minimum degree. Uh, oh yeah, here it says 128. Takes 100%, blah blah blah. And we won't start them. Okay, I'm reading from the internet again. I found something. Once an array tree, the height is also base number of elements. To determine number blah 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 based. Each node of entry is ordered between m and n except the root. A bit tree height grows logarithmic with the number of nodes it contains. More details about bit trees. Typically, an internal node has an array of each Bose diagram each 1,000 keys. There are 1,001 nodes at depth 1 over 1 million nodes at depth 2. Uh-huh. Let's, you know what, let's go with a small number so I can debug it, right? I don't have to create a lot of this. So k sorry, what is it? Okay, so for each node x is the key stored in the order in each node. If n in our tree, so t will be 2 for now. Okay. How it's called actually? Let's say it's a degree, right? So lower bound is a degree. So degree. That's how you write degree, right? Yeah, degree. Okay. So degree of 2. And I think, yeah. So we need to have, what's n? N is the upper bound, right? No, n is, sorry, what was it? What represents the upper bound? So I don't like what program is put in here. Between node. So I need num keys in this node, keys and children. Max children equals max keys plus 1. Wait, I found CS 280 on B-trees. Let's go and look at that. This thing. So first for page size of 4,000, this would yield max keys, max children 256, min children 128, min keys 127. Okay, nice. So in here, where is it? In here, I only need, for the B-tree node, I need number of keys in this node, max keys, and children. Why do I need num of keys? Num keys in this node. Okay. Oh, I guess. Yeah, I guess you don't have to. Okay. First of all, let's include an array. Instead of that, include array. Better than this, right? So stud array. I need max keys and max children. Max keys is 2t times 1, right? So wait, sorry, I forgot. Let's look at stud array. Let's look at stud array. Here, so type and size, right? So also forgot to switch back, but it's fine. So type is also node, so that's the children, right? Type and size, the maximum, right? So 2 times degree minus 1. The amount of keys. What's the amount of keys though? Wait, max keys 73, max children 74. Minimum children T 37 and 36. So minimum keys 36 plus 36 is 72 plus 1. Min children is minimum degree T. 37 is the minimum children. Maximum children is max keys plus 1. Okay, fuck it. Let's change it like that. So we have min keys, max keys. So let's go min keys. Right, min keys max keys will be equal to max keys will be equal to times 2. No, sorry. Minimum keys, minimum children. No, minimum children is minimum degree. 37. Okay. So let's min children. Okay. Min children. Min keys. So minimum keys is that's 3, right? Minimum children 3. No, 2. Minimum keys is 1. That's min children minus 1. Max children is max keys. Max keys is 340. Oh. Wait, oops, I'm not looking at this at the right one. Max keys. Okay. Oh, I am confusion. Wait. Or was it? Under the term minimum degree T. So the minimum oh my god, I lost it. Where is it? Here it is. Okay, so the minimum degree are the children, the minimum children. So mean children is 2. Higher. Not a man. Not a man. I'm using she, her, but I'm doing good. Thanks for asking. How your day is going? Yeah. I'm currently struggling with bee trees. 2 hours in. Okay, so min children is the minimum degree. Max children is max keys. So minimum degree will be 2. So minimum keys will be 1. Right? So min children minus 1. Max children is max keys. And what is max keys? 73. So 37 times 2 minus 1. So max keys is minimum children times 2 minus 1. And min keys, sorry, not min keys, and max children is max keys plus 1. So is, sorry, max, okay, I think I got it. Max children is max keys plus 1. Okay, and let's add the comments here. This is the degree, or in other words, degree, no, also known as T. Okay, and these are all based on this, on him. So, oh, sorry, I didn't give it a name. So this is the children, right? So children. Am I giving it the minimum children? I still haven't learned that structures in my courses, so I'm doing a bit slow. But when I'll get there, it will go easy. So I think it's good to learn now. Anyway, sorry. Where is it? Where is it? I'm sorry for the delay a bit, but what do I need to do? So the amount of keys is max keys and the amount of children is max children, right? So this is children, so it will be here max children. Sorry, and stud array node, not node, size t, right? Keys and max keys. Okay, I finally figured out the fields. In the constructor though, I need a key, right? And is it a leaf? I also need to insert non-full, right? I need insert not full, split child, and traverse. Traverse probably later. So, so void add not non full size t key. Is it size t? No, it should be int. Should be int. I think because it depends on the key, but it can be negative numbers, right? So let's go with int. So again, that was add non-full, insert non-full, split child and traverse. So insert. Let's go with this. Insert non-full and void. Yeah, split child. I'm always here checking with a tutorial. So I need a node. Right. And a node. I don't need a node. Or do I? Let's see. Damn it. Let's Wikipedia maybe. This is a lot to read, right? What I need is, well, first of all, that's not how we write split. How do I split children? Oh, it was in the insertion algorithm, right? Insertion, split children. So I try to insert 15, split. I guess I need the parent node. So yeah, split children. I need the parent node and what was it? The parent node and yeah, just the parent node. Do I need an index? Do I need an index? Wait, what the fuck? Insertion. Update the allowed number of keys in the node. Search the appropriate node for insertion. Focus B plus 3. And self-function which all present. Okay, whatever. I know it can have maximum. So that's deletion. I'm reading deletion. Oops. Insertion. Okay. Search appropriate node for insertion. Now there are elements greater than elements. So split at the median. Push the median key upwards and make. I don't need split children. Okay. This is what it will be for now. Okay, the B tree will have node root, right? Also I need and to add deconstructor. Never forget the deconstructor. Where is it? Okay. Okay, I just need the root and a bunch of... Yeah, okay. Just the root, just the root and a bunch of... Yeah, why does it have traverse? Okay, B3 insert. So I need an insert and a constructor, basically, that's it, right? So B3 constructor, it is empty, right? A deconstructor, B3, and what was it? Insert, void insert int key. Okay, I think this is sort of fine. Okay, b3.c2p include, we're going back, and then we're going into include, and then b. Okay, now the hard part. So first of all, node constructor. So let's node key and leaf int key bool is leaf, right? So yeah, okay. In here, is leaf, and where is it? Keys dot of insert here or something. I mean, I can. Oh my god. At back begin cn data mtn. Okay, I just key at 0, keys at 0 equals key. And oops, oh my god. And that also mean the children. I don't have children, so they all null. They're all. So do I need to? Yeah, I guess I can. Children dot fill null ptr. Right. I want to check stud array what class. Yeah, okay, I did it right? Correct? I'm telling here the size. Okay, so the constructor is fairly easy. Node I need to delete children and delete keys. No, just children. So delete children. Okay, insert non-full. Void node insert non-full. Just a key, right? Int key. Int key. Right, I need I need to go until I find until I find a key that is bigger, and then I insert it in there. I think I'll check again the pseudocode. Not exactly pseudo, but I'm not doing it exactly like that. So search on full in here I equals n minus 1. What? N minus 1 I and keys at I bigger than k. Yeah, I think I need num of keys. Int, where is it? Num of keys and num of children. So size d num of keys size t num of children. Right, so it's current, right? Current number of keys and current number of children, and here. Oops, not this. Yeah, save. Save. So size t index equals current num of keys minus 1. And here also I needed to I need to update current num of keys plus plus, and no, that I just can current num of keys will be 1 and current num of children will be 0. Okay, so size index and while index bigger is 0 and keys at index bigger than key, then keys at index plus 1 equals keys at index at index. Oh, and index minus minus. Index minus minus. And in here, keys at index equals e. Okay. Okay, can I just do for each here? No, right? Yeah, no, that's nah. Okay. That should be fine, right? Oh, and I need to update current number of keys plus plus. Right, I just added a new key. Okay, so that's insert not a full. I think it is fine. What? Wait, I'm looking at the implementation here, the tutorial. Is it I plus 1? Oh, wait. Right. Yeah, that's index plus 1 because it will be now at the point where it is less. Sorry, less than. Yeah. It will be something that is less than key. Technically less or equal, but I think I shouldn't have duplicate keys. So keys at index plus 1, index minus 1. If we get to 0 and it is still bigger, right, we still do index plus 1 at 1 equals the one at 0, and this is minus 1 now. And this is size D, so it's no good. It is a really good thing I noticed that size D will overflow and it will fuck up. Whew. Good thing. Shouldn't use size T willy-nilly, I guess. Fact that it can't go below 0 is, yeah. Okay, now. Split children. Split children. And that's a node. Okay. So I take the median, which will be wait. Sorry. Take the median, which will be children at the median will be children at keys at the median. So sorry, node. Wait. Yeah. Okay. What they did here. So new node. Yeah, that's the one we're splitting around, right? So keys at j equals Mm-hmm. Where yeah, we're copying. We need to left and right. We need to copy left and right. So we need to actually copy. Yeah, we need to copy the node, current node. So z keys j equals y plus t. Uh-huh. Um, if y leaf equals false, wait. Um, keys at j plus t. Right. Okay, so we're copying the left, the right keys. We're copying the right keys. Oh, yeah. And y leaf equals false. If it's not a leaf, then child at this equals, oh, and we're copying the children. If that's not a leaf, y n equals t minus 1. Print j equals n j da, da, da. Okay, so what we need to do here, yeah, but we need to erase the keys, right? So okay, first let's copy node. So that'll be left, right, left equals new node. What do I give it? A key and oh fuck, wait. I need to give it a key. Well, that's awkward. I need. No, it'll be okay. It'll be an empty node, right? It'll be an empty. So for now. So oh fuck! I still need to give it a key. How do I do it? How do I do it? How do I do it? Oh, I don't need to give it a key. What the fuck am I? Okay, yeah. I don't need to give it a key because we have insert. We have insert. No. The problem is it's have to have at least one key, right? So I can give it to the rightmost key of y. Not y, sorry, of my current one. So that'll be, what is it? That'll be keys at yeah, so okay, that'll be keys at 0. Sorry, and we need to give it where is it? Oh, yeah, I moved it. Int e. So this, and give it, if it is a leaf, true. No. It is a leaf if if current is leaf, so is leaf. Okay, so if current is leaf, it will be a leaf, right? I'm checking against this. Yeah, okay. So now I have a new node, and the median. Let's save the median. So int median equals current num of keys divided by 2. Sorry, I hope that wasn't loud. So median key. Let's go with median key. Median index. Sorry, median index. Median key index is current num of keys divided by 2. That'll be the median. So yeah, okay. So we have at 0 already. At 0? No, sorry. This will copy the right. The right? No, it's okay, yeah. I'm stupid. For each event, stood for each. I don't have, let's include here common HP. So stood for each. First will be left keys dot begin plus 1 because we already inserted the first key, plus 1 left keys dot begin plus current plus median key index minus 1 because I don't want to copy the median index. And wait, problem is I don't, yeah, it should be equal to, yeah, I think I need the regular 4 here, so yeah. 4 size t I equals 0, I is less than a median index plus I. Oh, so left keys at I, actually again it starts 1, right? So I have a 0. 1 equals keys at I. Oh. Okay. This is hard. This is hard to keep track of what I need to do. So, okay, I'm copying the keys. It shouldn't copy the median key, right? And then how do I split it actually? Wait. Oh, but it's not. Oh God. I am so confused because I need to bring it. I need to bring it up, right? So bring it up the tree. Tree. So in here in the pseudocode, it's from n to I plus 1 j minus minus. So that's not left, that's middle. Again, they have here in the insertion. Okay, in the insertion. How split children work? Just take the left and right. Oh, okay. We take left and right and add it to the middle. Yeah. Yes. Yes. Okay. So that's not left. That's middle. Right. Not left. Middle. Like median key index. So at median key index and is leaf. Actually, it won't be leaf. It's false because I'm splitting it. It won't be a key. And now I need to split it into two. Wait. I need to think. Yeah. Take the leftmost keys and the right. Take the left to the median, right to the median, and it will have two new children. Right. So So how do I move it? Okay, I do need to create here a node left and node right. Right, so or node, let's go with that. Node left equals node left. God damn it. This is hard. So, okay, let me collect my thoughts on it. I just want to split the keys, right? So now I need to write and to give two children. Yeah, two children. Which will be leftmost and rightmost. Should I give it maybe an array? Yeah, like give it an array of keys instead of one key, right? I think that's the way. Yeah. Okay, we created this, right? So we have its first key. Its first null key, and children fill null PTR. So I want to insert two children, each of which have keys from beginning to median -1 and from median +1 to end. Right, so what I need to do actually, I mean, I can create it and just give the 4. Or yeah, let's give it a stud array, right? Stud array of the same size. No, actually, no. Let's do it. Let's do it the old-fashioned way. I'm thinking about performance here. Okay. Problem is, I can pass an array here, right? I can pass an array here, and then I can just copy it, but I can also yeah, I'll just do it like that. So okay, middle children dot have insert here. No, let's add 0, right? 0 equals new node. And the keys will be keys at 0 and true. How do I know if that's a leaf or not? Sorry. Yeah. Ah. Okay. I moved in my chair. So how do I know if that's a leaf or not? I mean, it will become a leaf for this one, but then I move it up. How do I move it up even? Okay, yeah, I need to give it parent. So node parent. Oops. Parent, right? So, node parent. I'm sorry. And in here I insert how do I move it up? Right, I just insert in the parent one. So the problem making copies here. Can't I just move without making copies and stuff? I probably can, honestly. I probably can. Yeah. Pointers I'm just moving. I can just move pointers, right? So how will it work? How will it work? How will it work? Left. Okay. My current idea is giving the middle left and right, then moving the middle into the children of the parent. Right. What do I do with this, the current node? And you can probably replace this sage of isLeaf with something else you already have. With current implementation, replace the usage of isLeaf with something else you already have. With current implementation, you'll have to update the flag value with each insertion and removal of node from the tree. It might be overhead you'll prefer to avoid. Oh, yeah. Okay, I get it, I think. I, yeah, I'll probably replace it, but I'm still not 100% sure on what to do with, how it's called. Because do I have to copy actually? And what do I do with current node? Do I just delete it? Want to delete the rest of the tree? How do I move it? And Bully's leaf is probably going. Yeah. Um, is probably going. But I'm thinking currently how to copy, like just move. Maybe if I change it, I mean, still distinctly sort of, how do you call it? Sort of a pointer. Sorry, yeah, sort of a pointer. I can change it to pointers maybe, and just move like a list, right? Without actually needing to copy everything. I'm also not 100% sure how Stuttery works, so yeah. In sort of sorry. Oh, yeah, that was a nice message. Thank you. Just a second. What the fuck? Oh, okay. Sorry, I banned him. Okay. What can I what can I do here? This if I do it with pointers, how is actually? Yeah, I can. I guess I can use to move. Keys I will copy, and children I use to move. To move work, right? Let me check. I'll get efficient resources. Did another object. Because what happens with the instance of this, right? I'm copying the left, right keys, and then the left and right children. It is okay. It's supposed to have it's left children supposed to take care of the left keys and right children of the right keys, and the median is just will be the parent of those two blocks of children, right? So wait, no, what did I just say? No. It's much harder than anticipated, honestly. How can I do it? So in this example I'm looking at, it's not on the screen, but I went over it at the start. So I'm supposed to take the median key, bring it up, and create two new groups of children that are separated by the median key again. So one group is responsible for the left, and the other is responsible for the right group of keys, obviously. So, oh, first of all, let's remove this actually. And to give it something else, I think I need to check somehow if it's a child. But for now, let's just this, okay? So and I don't need to have this and this. So middle children 0. This is the node at 0, and let's say middle children at 1 is new node keys at 1. Sorry, not 1, at median key index plus 1. Right. What if I don't have... Wait. What if I don't have... No, I should have... Yeah, I should have more than 2, right? So if I have 3 divided by 2 is 1. Oh, I need to take the 2 then. If I have 3 keys, right? So number of keys divided by 2 is 3 divided by 2 is 1, so the median key index will be should I add plus 1 here maybe? This plus 1, right? So current number of, so if it's 3 divided by 2 plus 1, it's 2. So left will be 1 and right will be 3. Right. And if we have 4, and if we have 3, and left will be 2 keys and right will be 1 key. I think it's fine, right? Okay. So this at 0, and I think, yeah, this is supposed to be fine. Right. 4 divided, 3 divided by 2, and it's, okay. Now. I'll start with, I'll go from 1 to median key index, right? And middle children, middle children at 0 keys equal, keys at I equal middle, equal keys at I. Right. And push equals to the move. So can I now to Okay, yeah, stud move is okay. Stud move should be fine, right here. So, middle children 0 children at also I, right? I minus 1. Yeah, at I minus 1 equal would move should move children at I minus 1. Okay. Will it decrease the size? Huh? It will decrease the size, right? I'm not deleting it or something. Not the size of the current. Okay, no, it's fine. It's fine. It's fine. It won't move everything around. It's not a vector or something. Okay, so middle children at 1 keys at I plus I plus median key index, right? But and starts with 1. Plus 1. Equals keys at I plus median key index plus 1. And middle children at 1 children at I plus median key index plus 1 minus 1 equals children. Equals stud move. Stud move. Children at I plus median key index. Okay, I think I somewhat figured it out. So now we moved the children. Okay. Now the parent now the parent of this node. What is the type of children 0? Node. Pointer to node. Look at this. So that's an array of nodes, of pointer to nodes. So I am moving ownership of the pointer. I don't, because delete want to be good for me probably, right? So I thought of moving ownership now. If it's a pointer, you don't have to use stud move. You'll have the exact same effect of not using it. Yeah, I guess. I guess. Yeah, but what do I do with the parent? This you are correct. Yeah, I should. Yeah, it's a pointer. It is fine like that. I did it because I got confused on parent because I still need to remove somehow maybe. Um, oh no. Oh, okay. No. Okay, I know what I have to do. Okay, so node parent. Uh, node node parent have this as one of their children. Now, do I still have when we want to move big structures, for example, stud vector, stud map, or stud string? Yeah, yeah, that is right. Thanks for reminding me. Um, uh, it doesn't create a copy, I guess, right, with a pushback. Uh, so I still don't 100% understand stud move, but the problem, I think I need an index of the child here. Because middle, I'm changing. Wait, do I need the middle? Middle is. Ah, it is so confusing. B trees are confusing. B trees are confusing. Okay, I'm looking at a graph here of a B tree, and I'm trying to figure out how moving the current middle into the parent, right? So just calls the move constructor, so it doesn't have a move constructor. Oh, okay, got it. Thanks. It does not have a move constructor. The node class. Yeah. But how do I move current child at the middle? Because I created this and I should add it to the. Okay, let's think. What do I have here? I'm getting a node of keys, right? Um. Oh. Okay. Think I know. I think I understood it now. So I don't need to move anything. I just need to change because it's a bottom-up approach, right? So I'm starting with a leaf. No, that's. Oh. I'm also having a hard time to express what I'm thinking right now because my thoughts are all over the place about this. It's confusing. So, um, I'm taking the child. I'm splitting the array of keys into two different sections, and I add those arrays as children to the middle, and the middle should move upwards. It actually can move downwards, right? Or it always moves upwards. Okay. So I split the keys to two different arrays, right? Um, what am I supposed to do? I'm taking the keys. Oh, I don't. Wait. It can be more than 2 arrays. Insertion operation. That's search the node is full. Set the element in increasing order. Now there are elements. So split at the median. Push the median key upwards and make the left keys as a left child and the right keys as a right child. Oh, so wait, okay. So what I need to do, instead of whatever this is, parent doesn't think about and it to be easier to think about. Oh yeah, I have the operation. I mean, I didn't do it, but it's like this thing. Okay, I'm occasionally looking at it, but it's still kind of confusing. And thanks. Um. So should move the key upwards. If I'm moving the key upwards, this means that the key actually I'm starting with the right, so the key should. Am I starting with the right? So if I'm. Yeah, always start with bottom right. I'm the allowed number of keys of node. Search the appropriate node for insertion, so it can be left. Okay, right, it can be left. Makes sense. If the node is full, follow the steps below. So insert the elements in increasing order. Right, that's the insertion. Now there are elements greater than this limit, so split at the median. Push the median key upwards and make the left keys as left child and right keys as right child. So I need take the parent, right? Damn. I take the parent and search for where I found this. Right, and I can insert it in the middle, right? Or not. In the middle. So yeah. Well, again, confusion. I am confusion. I'm taking. I'm going. Okay. I'm going. I just need to move the key. Insert non-full. Right. On the parent. The keys. Huh? No. Wait. No. Insert non-full. Yeah. Insert non-full. The median key. Right. This one. The median key. And then make how do I split the children though? 2. Mm, Okay. If I just move the key upwards. If I just move the key upwards, will it do anything? Because I'm like, just move it, remove it from the array. I have the left part and the right part. And left, right, have left part, right part. Yeah, but now I have one less key. So which of the children go? And the children won't go. Why would the children go? And make left keys as left child, and right keys as the right child. So the node. Insert the node in increasing order. Insert the node in increasing order. Wait. Trying to visualize it in my head and it's not going well. So when I move the key up, when I move the key up, these children become the children of the parent, right? So I'll need to insert into the children into the parents one, but I need to do it. So I need insert node, I think, right? I need insert node. I need insert node. Let's look again at the code here. I can bring it back. Actually, why not? So, what is it? Insert split child. So split, not insert, split child. So I'm guessing this is the parent, right? This is the middle. T and leave whatever. Ta ta ta. So keys. This keys is y keys j plus t. Y keys. Why are the parents? What? If I'm assuming this y is the parent, right? Assuming y is the parent here. So z is at j, so say 0 at t minus till t minus 1, y keys at j plus t. If while if equals false, that's the only one. Okay, so I'm guessing this is the median, right? I'm guessing this is the median, t minus 1 and j plus t, so j plus t, right? So t minus 1 is the median, should be the median. So till median, okay. And n and bigger than I plus 1, I minus, j minus minus, cj plus 1, the children. Oh my god. The children, j plus 1, moving the children right, and the I plus 1 equals z. Okay. What is n? N is the order. Okay. N is the order. So in here, int I, node y, split children. How does it starts? J equals n until j is then I plus 1, j minus minus. Right, moving the children, like moving children to the right and inserting okay. Let's think. I've been doing it too much, honestly. So middle children are. I don't think this is what I want to do. I have parent node. Right. Parent node. If I split this, I need to insert I need to insert the middle. Middle? No. Sorry. I need to insert the key. Okay. I need to move the key up. So why no parent insert non-full key. Okay. Then after inserting the key, I need to move the children, insert the children. Right. So let's do insert children. Void insert children. Children. Wait. Set children. Okay. How do I do it? I have, let's say, I have an array of children. I want to insert them in the where I inserted the key. Right. And so when I inserted the key, so I'll move children to the right, insert non on full children, right? And I need a stud array of node max children. Okay. I want to insert this. Oops. I want to insert this this array in the middle of this array. In the middle. Yeah. Let's give it an index. Int index, or a range, more like, right? In the range. No, int index where starts to insert. Let's start index. I think it can even be private, right? Because I will be only using it inside the split children. So void node okay. Why does it look so annoying? Why does it look so annoying? God damn it. Okay. Whatever. That's my formatter at Windows, sadly. So, okay, so I've start index, it's like size t, right? Size t. So, what do I do? Start for int I equals 0, not 0, sorry. I equals current num of children, right? I did tuck insert on full, so a while. It's a while here, so while so I'll have my int current index equals current num of children, right? Yeah, okay, so this, and while current index is bigger equal than start index, let's give it an int. Start index can be it can be -1, but I need to do this with -1, so I guess well, then start index. Then what I do is children, this children, this children, this children at current index. That's -1, right? -1, so at current index +1 equals to this it starts no oops sorry it's supposed to start from current index supposed to start from current num of children -1 but bigger equal than start index plus children dot size. Okay. Right, so I have place, right? So bigger equal size -1, I think, right? -1, because I need to, let's say I have an array of 4, and I need to include another 2 in the middle, let's say between 2 and 3. So my start index is 1. I have 1, 2, 3, 4, right? So my start is 1. The size is 2 of what I want to insert. So the size is 2, the index is 1, size is 2. So 4 is at index 3, obviously. So I start at index 3. And I want to move 4 and 3. Oh, but I need to move them far enough away, not just by 1. So 5. Okay. Think I get it, I hope. Okay, let me try and explain what I thought about. So we have the size, right? We need to make room for the new array. So we just need to move. So again, if it's 1, 2, 3, 4, and I want to include another like 5, 6 between 2 and 3. So I need to move. So 0, 1. So 2 and 3 needs to be moved. Each of them need to be moved. I mean, indexes 2 and 3 need to be moved to indexes 4 and 5. Great, 4 and 5, which is the size of this. So current index is, say, it's 3, and it is bigger equal than start index plus size. So it is bigger equal. So again, in my example, it's 3. It is bigger equal than index 1 plus size index 1. No. Okay, it's bigger equal than start index, right? So again, start index should be 0, 1, 0, 1, 2. Start index should be 2. Again, in my example, start index should be 2. 2. No, sorry, start index should be 1. Yeah, that's, again, I'm doing 1, 2, 3, 4. So start index should be 1. But no, it should be 2, right? I want to between 2 and 3, so between the numbers 2 and 3, so between index 1 and 2, so it will be on index 2. So start index is 2, and while current index is bigger or equal than it. Okay, yeah. But not +1, plus children.size. This children equals 2 this children at index. Figured it out. And the current index minus minus. After this, we just insert it. So for int I equals start index, I less equals then. So again, I want to insert now at indexes. We have 2 and 3. And 3 is 2 plus size minus 1. Or so start index plus children size. And plus plus I and children this children at I equals children at I at 0, like 0, right? So yeah, I'm already too confused about this, so I'm thinking a bit slowly. But int I equals start index from start index. So to make it 0, right? So I went to 0, then 1, 2, blah blah blah. If I start with an offset of 3. Oh, so I started with the start index. Or I, sorry, I minus start index. Okay, figured it out again. Right, so yeah, so first it will be 0 and da 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 da. Okay. Okay. And this should be enough to move it, right? Yeah. So in here, in here, what I do is move the key up, right? Remove the key from here. So let's delete this. So let's int median key index and median key, I guess. Int median key equals keys at median key index. Right. So now or oh, and after this, I update the current num of children plus equals children.size. Right. Okay. Now int median key. This keys at da da da. Now I delete the key, right? So for I can't for each actually. This one stood for each. Stood for each. I'm deleting something. Do I have fine. Keys dot gain keys dot end -1, right? Not end -1, sorry. begin plus current num of keys minus 1 and capture list is this. I'm getting the int key, right? And in here, I'm just wait. How do I do it? How do I do it with for each? So yeah. Yes. Int key. This int key should be equals to the key after it. I don't think it's doable with for each. Maybe with other like library function, but I'll do it with a regular for, I guess. For int I equals median key index I less than that num of keys. That's what's I. Right. Minus 1, I guess, right? Minus 1. So, sorry, not current. Keys at I equals keys at I plus 1 and current num of keys minus minus. Okay. Now lead this now. Parent it will be the start index for this one. Shit. What will be the start index for this one? How do I move it? Oh my god. So I need to move it to the parents, but how do I decide actually how to move the children there? Sorry, I mean split. It will have. I'm guessing. Okay, wait. Okay. Oh wait, I don't move all the I don't. Yeah, I am. Right, I need two. I need to take. Oh, I need. So split it into two. Right, move current key. The median key. Sorry, I'll move it up. it's fairly easy, right? Insert non-full, insert non-full key, and just insert, easy peasy, right? But what about the children? What about the children? How do I insert them? Technically the children are already. This is already right. Okay. This is one child, and it just turns into two children. It's not. Yeah. Okay. So actually, okay. Not an array. Not an array. Just node left child and node right child. Start index. No, not the original child. Node original child. Oops. How do I? Okay. So here, like that. Okay, and I need to find the index of the current child, right? So I need to find the index. Yeah. Yeah, int index equals 0 while let's remove it. Okay, so while so I just need to find the index, right? I can't just do a regular for or while, but maybe I like for each, but is there a find like a children dot? There is a stud find, right? Stud find gives me the how it's called, iterator to whatever it found. Gives an iterator to whatever it found. Yeah, and then from there, okay, I'll have an iterator, and then I can let's try it at least. Maybe wait, auto it equals children stud find children dot begin children dot begin plus random num of children -1 and original child. Okay, I found this. So while I can just for it is not equal to okay, so I have it so just in this and the second one. So oh wait, auto it or original child it, and this should be auto fuck it, just iter auto iter equals to children dot begin plus current num of children minus 1, right? And well, iter not equals to original child it, what is not child, and iter minus minus. Oh wait, I got yeah, I can't move stuff with iterators. I can change them, but I can't move. Well, that was an attempt. That was an attempt for sure. So let's find the index bucket. Int index equals 0 for int I. Well, I'm getting index while actually while children at index not equal to original child. Wait. No, okay. That's fine. So children at index not equal to original child. Not equal to original child. I guess. Now I want an error to raise if, right? So while this is not equal to original child, index plus plus, right? Let's go if index equals then current number of children, throw 1. Nah, it's fine. I think it will just throw an error anyway, because I'll try to access it later. I think. Nah, I don't want to fuck up something in the like without a crash. Okay, so I found it. I have the index of the child, the original child. So now int current index equals current number of children minus 1 while current index bigger, right? Well, it's bigger. Bigger equals, I guess. Then index plus 1, because I want to add another one, right? Let's bring in bigger index plus 1. Yeah, bigger equals. So, right, yeah, okay. Bigger equals, and then current children at current index plus 1 equals to children at current index minus minus. Okay, and now I just have to insert those two children. So children at index equals left child, children at index plus 1 equals right child. And that's it with this. So now, now, okay. Now I need left child and right, and create the left child, right child, right? So the left is to the left of the median and right is to the right of the median. And they all have different. Okay. Do I need to create new heap allocations and stuff like that? I have. Okay. If I have left and right, how do I? There's not really a way without copying. I guess I can. Okay. So node so oof. Current index. Also and no children plus plus. So node and it creates left and right. That will take care of the right, left part and right part of the how would I do it? Left and right, left and right. So I have the key. Now I need to create a new node. No, I don't need to create. I'll move the key up. But now I need to create left and right, left and right, left and right, left and right. And the original is this. This doesn't have median keys. Is that fine? Yeah, that's fine. Right? Yeah. So I guess we're gonna go left. Hmm. Okay. Node left equals new node key. So the key will be at 0, right? So keys at 0. On left is keys at 0 and node right equals new node keys at median key index. Median key index is now the right part. So at median key index. Median key index. Okay, so for int I equals 0, I is less equals even, right? Median key index, no, less than median key index plus I. Now left keys at I equals keys keys at I, right? Left children at I equals children at I. Actually, that starts with 1, I guess, right? So, right, that's the left one, and the right one is right keys at I plus median key index equals keys at I plus median key index. And right children at I plus median key in, wait, Joe. Oh, now I have the same amount of children and keys, so that's fine. That should be fine. Was keys at keys equals children at I plus median key index. And I need to update their children count, right? So left current number of children equals that was from 0 median key index amount. So the amount of children will be median key index, right? So if we have from 0 to 3, the median key index is 4, right? So it's less than maybe 1, 2, 3, 4, right? So that's median key index. Key index and left current num of keys also should be equal to, wait, isn't, yeah, Right. I plus median key index 1, and this is -1. Yeah, and this is this one. Right, okay. So left current number of children is median key index -1, and the number of keys is median key index. And let's just copy it. And it's right. Okay, we updated the numbers. Now I have left, right, and current, right? So we do parent insert non-full median key, and parent insert non-full children. This left child, left and right. Okay. Right. What happened though? What happened to original child here? So children at index is the original child. If I delete the original child, it will cause a chain of destructors, right? So of all its children, which is no good. But don't want that memory address to be occupied. That's a memory leak. What do I do here though? Original child. Wait. Original child will be the left child, right? And the right child will be the new one. Okay, so I don't need to create two left and right. This is the original, right? So I'll just do... Okay. I have an idea and it is a solid one. Fuck. So what shall I do? It will be like that. I need the just right, and the left will be from 0 to 2. Okay. So I don't need left. Just need right. Right equals I equals to median key index plus 1. I is less than amount current now of children plus I. Okay, write keys at I equals to keys at I I minus 1. Minus 1? Wait. Right, keys I, sorry, I minus median key index. This one. Right? Right, keys at I equal to keys at I minus this one. Okay. Right, what about the children? What about the children? Children, easy. Right. Children. Right, children at I minus 1 equals to keys at I minus median key index plus 1 minus 1. So like that. And after that, current num of keys equals current num of keys equals I cut them in half, right? So it is divided by 2? 3, let's say 3. So 2. Okay. Let's see if I have, okay, if I have an even, then I have to add 1. If I if 0, 1, 2, 3. Yeah, if I have an even, I have to add 1. If I have even amount, then I have to add 1. If I have uneven, let's say we have 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4. And we take 0, 1, 2. We take 2, right? So it will be with 5 divided by 2 is 2 plus 1 is 3, right? So the median key index will be 3 if I have from 0 to 4. 3? Wait. 5 divided by 2 is 2. Right. The index is 3. God, I'm getting confused. Okay, I have indexes 1, 2, 3, 4. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Right? Okay. I have 5 keys. I'm using fingers to count. 5 keys divided by 2 is, we'll round it to 2 keys. 2 plus 1 is 3 keys, right? 3, index 3. Index 3. Wait. I don't want this plus 1, do I? Yeah. So 5 divided by 2 is 2 plus 1 is 3. This is the index. I want the index 2, 5. But what if it's 4? It's 4 divided by 2 is 2. So 1, 0, 1, 2. Right. Problem is when I have 2 keys. So median key will be at index 1. And this is... I'll deal with it later. For now, this is fine with the median key index, it's fine. So current num of keys, I ran from median key index basically, current num of children. So it will be current num of children minus median key index, right? Is it correct? It will be current num of trying to visualize it because it's kind of the problem is it can be off by 1 here, a bug off by 1, and I don't want it. So current num of keys equal to current num of children. So say we have 5 children, median key with 5 children, it will be median key will be 2, median key index will be 2. So 5 minus 2 is 3. 3. So I have, yeah, from 2, 3, and 4. It's 3 and 0, 1, and 0, 1. Wait, what? 0, 1, 2, 3, 4. Okay. Let's do that later, right? Let's remove the key later. Okay, let's do it later. So in here I still have the median key index, right? So I start from, right, it will be plus 1, right? And this start from plus 2. Okay, I'll do that. Okay. Now, what the amount of children do I have? Current number. Sorry, the amount of keys I have now. I should have half of the keys. So let's say again, let's say I have 0, 1, 2, 3, 4. I do the 5 divided by 2 is 2. So 2 is this, right? Okay, but what if we have an even number? If we have an even number, say from 0 to 5, right? So that's 6. 6 divided by 2 is 3. So 4, 5, the right will be minus 1. The left will have the 3. So this current number of, not this. Yeah, this current number of keys will always have median key index. The right is a bit problematic because if it is an even number, if current number of keys is even, then I can just, you know, check like if it's an even number or not, right? Is necessary? I guess so. This is not necessary though. This, not this. If current num of keys modulo 2 equals 0, then write current num of keys equals median key index minus 1. Else write current num of keys equals median index. Okay. And current num of keys. Okay. And then we remove the median key, and then we insert non-full, and then original and right. I don't need left, so like this here, original and right. So original and right. Da da da. So find the original. Okay, int current index equals current num of children minus 1. Plus index plus 1. Yeah, I move it by 1, but children at current index. Nice, and children at index doesn't change, but children at index plus 1 change to right child. And current num of children. Yeah. Okay. So this end right. And now insert median key. Wait, is this it? I insert the median key. I insert right. Is it okay now? Is it okay? That's right. We have now and the key should be fine, I guess. Now I need to take not even edge cases, right? That's kind of part of this. So if split children is fine, but insert non-full children. No, I think it should be just insert children, right? Now, if this is full, then I split this one. Okay, so let's do like this. If current number of children equals max children, then if it is a root, then I create a new root, right? and split around it. First of all, let's wait, how do I know if it's a root? Maybe problem here in split children, right? When I do insert non-full children, I can go above the maximum amount, and I need to check that. How do I check that though? It's fun. How do I provide a parent even? How do I provide a parent? I think this should be done inside the B tree structure. What? 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 Ah. Wait. What? Can't. If I do it inside the B tree structure, I'll have to. Yeah, okay, let's do it inside the B tree structure. So technically, they should be working, right? I think. I can only check it after I complete this one also. But yeah. Okay, okay. Boom. Let's try and do. I don't know how much more time I will be doing this today, but I'll try to be quick about it. B3. Yes, root equals R. And B3 delete. Okay, now insert void B3 insert int key. Wait, what about the node? Oh no, it creates a new node here now. Split children. No, I'll create a new node. Okay. First of all, I need to check if this is a root. If root equals null ptr. If root equals null ptr, then I'll just doing root equals new node and give it a key. And that's it. Else, what I'll be doing is I need to go and to go down the tree, right? Go down the tree, find where should I insert the key. Okay. Let's just do this and return. I don't want everything in a else statement. Okay, so int I equals 0 while Wait. He. I won't. Let's check with the root. Then with children. But how? Um. New node maybe? Should I create a new node with the key? I create a new node with the key. No, wait. Yeah, I need to pass in here. I need to pass in here a node. Like where should I check, right? Node. Current node. And first I will be passing the root, right? So while current node current node children wait, children, sorry, current node keys is bigger than key. Oops, current node keys at I is bigger than key, then what I'll be doing is that bigger than key, then just I plus plus, right? I also need to check for out of bounds. Should I? And yeah, I less equals then current yeah, current node. Oh my god. Current node current amount of keys. And this. Okay. I plus plus. If key. So I found an I. I think less, right? Less. If every key is if every key is bigger, then this is the smallest one. Oh no, wait, what am I doing? I'm doing from smallest to from smallest to so less than, right? Now if it is the biggest key in there. Oh, that's fine. Okay, that's fine. When I found mice, then just insert Oh, I need to find a leaf. Right. I have to insert inside a leaf. So I need to check if that's a leaf. If current node children current node current num of children equals to 0, then it's a leaf, and then I can insert inside current node. So okay, check if it is full. If current node current num of keys equals should be equals max node, right? Node max keys, then I need to split children. Wait, how would I give it a parent though? How can I give it a parent? Parent. How can I give it a parent? Current node, current number of keys, and I need to split children. If it is magnitude landmarks give need to pass in the parent. So inside insert I also pass the parent? Right. I guess so. Int key node current node parent. Copy paste. Okay, so if it is bigger than split, then parent node split children parent. Yay. And now split children parent. Now wait. In split children here, I need to check if parent is full. I need to split parent, but I don't know the parent of the parent. How would I know the parent of a parent? I am. How would I know the parent of a parent? I guess I can traverse Thorf, right? I need to traverse it. I need to. if the number of keys is maximum, blah, blah, blah. Then I need to call split children on the parent. Why? I need to know the parent's parent. I need to know my grandparent to do that. Right? Yeah. Yeah, I do. So, what should I do? Parent. I can search for the parent, I guess, right? Can search for the parent. That's an idea, I guess, but wouldn't it be too long? Wouldn't it be too long? Wait. Confusion. Yeah. Oh, maybe, wait. Certain. What the hell? Hmm. Okay, here I'm finding the leaf, right? Finding the leaf. So this is a leaf, and here I split children. But what if I wait? What if I reach max children? Let's say if I reach max children, then I automatically split, right? Can it be split parent? Okay, so current node, current name of keys. If it's a leaf, it's a leaf. Right. Split children. After the split children, if the parent is full. If the parent is full. Oh. Oh, what if the parent is full? What if I can't add another child to the parent? Can it happen that the parent will be full? Oh my god, so annoying. Okay, so current node, bigger equal than node max keys. Current node, split children, parent. This is a problem. Because if after the split, so I need to do it here maybe, right? Set full. Oh, wait. Yeah. Insert children. Okay, let's change the name. So insert children. If I don't know the fucking parent, right? Don't know the parent. Full. I want to I want to split children, but I don't know parent. This is a problem. This is a problem. This is a problem. Split children with its parent. How do I give the parent of a parent? I can maybe have double, like give child to. I can add here. Where is it? Here, I can add here each node to have its parent, right? So node parents. Each node has its parent. Outside of the root. So on creation though, I need to pass node parents. Okay, so where is it? Known parent, so key and parent. Right, okay. So now I always have a parent. Insert children. If parent name of children Make that max children. Then split children. Parent. Right, if it is not, then do that. I think it's fine, right? It should be fine. So if it is split children calls, oh, insert children. Split children calls insert children. Right? It will call this. Also, I can just delete this, right? I can just delete this. Right. And here, obviously, right? So split children on this. Right, it's its own parent, should be fine. And after we're done, I hope it works. It sounds like it works. I don't think it actually works, but the recursion here is like split children. It reaches someone with place, right? Takes out the key, passes it up to the parent. Yup. I mean, it should work. Also, root is here. It's now tr. It doesn't have a parent. So, yep. Oh, and delete children and delete parent. Problem on root, it will call delete null ptr. So no. No, I want to be deleting parent, right? I shouldn't be deleting parent. Yeah. 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 We'll be deleting parent on its way up or down, I guess, right? So in here, split children. Current node split children. I know what the parent of the current node is. Do I need this? I think so, right? No, I don't. So current node split children. Else insert else current node insert non-full key, and we're done. Right, that's if I'm at a leaf. Now here well, okay, so less than current node, current number of keys, and current node keys at I I++. Right, I++. Then if it reaches the current num of keys, it will be one above. Right, it won't one above. Okay, so after this one, I want to insert, right? Call insert key on the child with the index. Wait. So I found a key that is bigger than my current key. Maybe I should actually change it to smaller. I found the smallest. No, wait, they are in ascending order. So I find this. And child I-1. Or if it's I-1, if it's a 0.0, like first key is bigger. Because it's ascending order, I need to be bigger, right? While it's, yeah, okay. But if it is the smallest key, 0, then I want to take, I'm guessing, the first child. Let me see. So it is bigger. I want to take the right. Oh my god. So, sorry. Right. Okay, the right is bigger and the left is smaller. So when I find the bigger, not just the right, like if we have 3, so okay, let's see, that's 0, 1, 2. 0, 1. Well, it is while it's smaller. So 0, 1. And this is +1. Wait, we have more children. Ow! Why? We have more children than keys, right? Slit children. A minus median index. Right. because I removed the child. Why trees gotta be so confusing, man? Why? Why? Oh, so this should be moved here. Why trees gotta be so confusing, especially B trees? God damn. God damn. So children, supposed to be bigger equal than keys. In here. Children I minus 1. Zero and minus median key. So say I have, okay, I have 2 keys, 3 children. 2 keys, 3 children. So this goes up to 1, right? Where is it? Oh my god, I lost it. Plus 2. Three divided by, what the fuck? Okay, so 3 divided by 2 is 1. Okay. So I'm where is it? Current number of children. It's 1 plus 2, that's 3. That want to go into here. It's 3 is not less than 3. So right will be less equal. Maybe less equal. Right, children. I minus 1. And we have I and 0 equals to let's say it's equal. Okay, so on 0 that'll be if we have 2 keys and 3 children. So 0 will be right median key index plus 1. Okay, yeah. Oh, right. Because of that. Right, but right children is a problem. 3. The rightmost child. So I need a different 4, I think, for the children. Right, so 4 I equals median key index, right? Or even split children. That's equals median key index. Key index will be, what's median key index? Index I is less than, that's current number of children. So that starts, again, if I have 2 keys, 3 children, that starts at +2. Wait, the fuck, +2? I think +1. When I know I have this, so again, 3 children, median key index, I have 2 keys divided by 2 is 1. So the median is 1. Should be this -1 maybe? Anyway. I think if I do this divided by this -1, so -1 divided by 2. So median key index, okay, +1 will be, so again, current number of keys is 2, we said, -1 is 1, divided by 2 is 0. No. Okay, we'll do it like that. So, okay, 2 keys divided by 2 is 1, so the index is 1. Starts at 1, +1 it's 2. That's the last child, right? I is less than current number of children. It is, right? So right keys I. So right keys should be right 2 minus median key index. Again, we're at 2, I said, right? So wait, 1. Well, 1 plus 1 is 2, right? So 2 minus 1 is 1 plus 1 is 2. Those keys 2. So no, that's not +1. That's, again, with 2 keys, 2 minus 1 is 1. Okay, and this should be +1, I think. It's children I -1, so children, and now we have 3 children, so 2 minus 1 is 1. Children 1. Right. The right. Okay. It's fine. Okay, and then 2 minus 1 is and -1, I guess. No. Ah, my god. What the fuck? What keys? Children. Almost fucked this up. So children of I -1 and of I -1. So again, with 1, 2, 3 children, and we had hidden key is 1. If median key is 1, then it's 0. But that's plus 1. So we're at 1. 1 equals children at I minus. So I minus 1. So I is 2 minus 1 plus 1. This off by 1 is fucking annoying. Holy shit. So, again, right children, I minus 1 equals. And I'm starting with 1 for the right. So I want children number 1 and 2. Okay? Let's say 1 and 2. So I will be 2, because it's median plus 1. So 2 divided by 2 is 1 plus 1 is 2. Okay. Minus 1 though at 1, right? So 2 minus 1 equals children at I supposed to start with 0, by the way, so that's right children is I minus median key index. Median key index minus 1. So at 0 will be the one at median key index, I minus median key index plus 1. This is technically minus 1, right? So this is at 2 goes to 2 minus 0. Oh, again, this is supposed to be switched. This and I here. I minus median key index minus 1. This is 0 equals to keys at 2. 2 plus 1. We don't have a 2. I minus 1? I minus 1, right. This I minus median key. This is the children. So again, I minus median key index, not minus 1, I don't think, right? So again, we're at 2. No, I need to, yeah, I need to get to 0. So that's 0. 1. Oh, but this is just I plus 1. I plus 1. So 0, 1, 2, I plus 1. Or just I. Okay, I think I solved this one, at least. Oh my god. I mean, I haven't tested. I probably didn't. It's probably not working, but you know, I'll fix it when I try to run all of this. Okay, so if not, insert non-full. Fine. Else, okay, and here return I plus I'm searching for a key that is bigger. Right, when I find one, I go right. And what is right? It's the children at I think, right? So I got index, right? So if I find something that is yeah, well, it's bigger, proceed, and when you find the one that is bigger than this, then go right. Start. Cert key, and I'll pass in current node children at I. Okay. Cert current node children at I. Okay. Bigger than key. What if it is the smallest? At 0. Key current node. No, yeah, that'll be fine. That'll be fine, I think. Insert. I think this is it. Not sure though. Not sure. But I think this is it. So if it's a leaf, max is else, just insert non-full. Right. Else, insert non-full. I 0. At I. What if it is the biggest key? Then I have to go the most right child, which will be at I plus 1. If there's a small stays 0. I'm guessing less equal. Okay. One less equal. And current key. Yes. Current node keys at I bigger than key. So if it's the biggest, it will still go one more. Okay, that should be fine. Third, and yeah. I think this is mostly done. Now I need to run, like, create a V tree and run some fucking tests and whatnot. But the V tree sort of done, I guess. Probably doesn't work everywhere and stuff. My main concern is keeping track of the amount of children. So current number of keys will be equal to median. Again, let's take the two keys, 3 children, an example. So 2 keys, 3 children. We'll have 18 in the most right. Sorry, most right as the key. So we have 1 key. Median key index is 1. So median key index is 1. So the amount should be minus this. This should be plus 1. Okay. I equals median key index, current number of keys. Now I'm right. I'm erasing the median key. And the current number of keys will be median key index. Current number of keys will be median key index. This, I am the left one, right? So, oh, I know. Why am I? Will be current amount of keys, current number of keys minus right current amount of keys. Same with children. Same with children that I did not update here. Current amount of children. Oh, wait. That's only keys. In insert children, I am doing that, right? Oh, I am splitting. Yeah, I should update the current amount of children. Also, this is not correct. Yeah. What the fuck is that? Oh. So, yep, I don't need this and this and this. And this is current number of children. And this is current number of children equals current number of children. So what the fuck am I doing? This is minus equals. And this is also minus equals right. Current amount of children. Okay, so I think I'm good with the amounts, right? Insert not full. Original and right, median key. Parent insert not full. Do I know that the parent is not full? First of all, insert children, then insert non full. Wait. That is enough for today, I think. I'm sure it mostly works. I will run a test next stream. So, because I need to write the test, right? But yep, 96 lines of code took me 5.5 hours almost. Nice. But I understand the logic behind it at least, so at a very edge case, I can just rewrite it again with better understanding, but I think it works. I think it works mostly. Definitely. 100%. Alright. That'll be it. Thanks everyone for tuning in, and if you have questions or something, leave them in the comments below. Thanks for watching, and have a good one. Bye bye.